xvn and xv prime n roughly look like the logarithm of the distance between v and v prime for any element v and v prime of the matrix. So, and in particular, we have a rather slow decay of correlation. And we will actually see that these correlations will affect the behavior of the system that we study, and that it's no longer true that these things look exactly as if they were completely independent. So let me just start by giving you some examples. And to some of these examples, we will come back in more detail tomorrow and on Thursday, maybe also today. And some I will just mention so that you know that they exist. So the first example, and I will just list them, and I will not really explain to you in huge detail why they belong to this class of log correlated fields, but rather just give you the list. So the first example that's usually given on this list is the binary branching random walk. And we look at it in the Gaussian case, so with Gaussian increments. So what is this process? So we just take a binary tree. And we do this with n generations. So we have 2 to the n leads. And so this is just a binary tree. And now what we do is we put on each of the edges independent n01 distributed weights. So on each edge of this tree, we put independent quantity distributed Gaussians with mean 0 and 1. And now we take Vn to be the set of all leaves. And we define our stochastic process xv of n for the element of Vn as just the sum of the weights on the path to the root. So if I take, for instance, this one, then I would just go back to the root, and then I would sum up all the weights that I find along this path. Now, for each v, this is of course now as a sum of Gaussian, a mean zero variance n Gaussian variables. So we have a collection of 2 to the n and 0 n Gaussian variables, but of course we have a correlation. Namely, if I look at two leaves xvn and xvn prime and xv prime n, then these are correlated. Because if I look, if I take a second, this one, and this path might now do something like this, right? Then these two paths to the root, they share edges, right? And if they share an edge, then in this sum, I sum exactly the same Gaussian random variable. And so the correlation between, if I take two leaves between the values of this stochastic process, this correlation is exactly given by, and since I have n0 ones, is exactly given by the number of edges that the path share. So this is given by the number of edges that the path from V to the root, and the path from V prime to the root. Sure. And this is also, this we're going to, that we could also, for instance, denote by the wedge V prime. And this is sometimes also called the overlap of V and V prime, or also the branching time. And usually this is a very prototypical model for log correlated fields. I must admit, it's not very obvious from this definition why it's log correlated, but one can argue this, that it's in this class of models. And what makes this model particularly nice? Well, this model is particularly easy. Right? So this is in the following sense, because it has a lot of nice properties. And what are the nice properties that are of interest to the questions we will be looking at later? Well, first of all, if you look at this xv of n, it's a sum of independent identically distributed random variables. So you always, if you just look at one particle or at one leaf, you always have a decomposition in independent increments, which is very useful if you actually want to do some kind of computation. Second of all, this point where you branch, this branching time, is somehow very explicit. So there is, if I look at two leaves, there is a time, right? So if I look at this time, then I know that before this time I share all the edges, so I have full dependence of the increments. that I use. And after, the increments that I use are completely independent. Right? This is something that you might not have in all models, but this makes it, this is a very nice feature to decouple things from the part where things are dependent and the part where things are completely independent. And a third thing that's very useful is actually that you have a certain self-similarity. Namely, if I look at some level of this tree K, right, and I start from there, I want to go up to a time n, then I see, what I see is, I see 2 to the k copies of branching random walks that are still running for a time or up to time, so which are still going, so that in total I have n generations. So these have n minus k. Right, and right, I mean, one might need to add a factor 2 somewhere, but essentially the idea is, well, if I have this, so if I look at this time k, right, then from each one here, I can just start a new branching random walk. And the ones, and here's level n minus k. So from each leaf that I have at this level k, I can start a new branching random walk. And all of these new branching random walks that I start are independent from each other. And the only connection that they have is that there is this part that kind of glues them together from the beginning of these first k levels. So if I look again in this in the subparts of this model, somehow I find exactly a branching random walk again. And this is another very useful property. Another example, which I would like to mention, which is very much in this, which is kind of the continuous analog of this branching random walk, is branching Brownian motion. And it has very much the same properties, but it's a continuous time version. So what you do is you start with one Brownian motion at 0. You let it run for an exponential 1 time to split in 2. So let's say here's 0. I wiggle around, I'm the Brownian motion. Here is my first branching point. Now I become 2. Maybe use a different color. So now I become 2. And now these 2 new Brownian motions. So, and now, so I become 2 particles, and these new particles form independent Brownian motions from where they split. And then they also split again after an exponential 1 time So they have the same splitting. So for instance, let's say the blue particle split here, then I get again 2 independent Brownian motions here. And the orange one might have lived a little longer alone before it split. And then I get 2 independent Brownian motions from here and so on. Right, so it's very similar to the branching random walk, only that now I don't jump always by one time, but I connect somehow these. So I make the waiting times until I branch exponentially distributed to make it a continuous time Markov process. And then I connect the different values somehow that I get at each generations by Brownian motions. And so in this model, I have at time t, I have a random number n of t particles. And one can show that actually the expected number of particles is given by e to the t. And you have locations of the particles xk of t at time t. And of course, if I just look at one of them, right, it's just the path of a Brownian motion. So each one of them is just a Gaussian at time t with mean 0 and variance t. So in some sense, I have e to the t Gaussians, which all have variance t. And this is it's really very similar to what I had in the binary branching random walk, only that instead of having powers of 2, now I have this number e appearing. Another example which falls in this class of log correlated fields, which I also would like to mention, is the 2-dimensional discrete Gaussian field, which is now a model that which doesn't live on a tree or the leaves of the tree, but this metric space that we take Vn is actually just some finite square of the integer lattice in 2 dimensions. And now we get the 2-dimensional discrete Gaussian field as a Gaussian process indexed by the elements of Vn that has mean 0 and a certain covariance that is given by the Green's function of the simple random walk. So if I say that PV should be the law of a simple random walk S starting from V in the N, and I denote by E of V the corresponding expectation and I call tau n the exit time of Vn, then I can define the discrete Gaussian free field xv of n. V in Vn. Right? And I will be slightly sloppy here about what the n exactly is. I mean, the Vn, this little n here should be somehow connected to the size of the box. So indicating I'm more mentioning this out of completeness here, so I will not, not spend too much time on this discrete Gaussian free field. So let me be slightly sloppy here. So we look at xvn. N should be a Gaussian process with mean 0 and the covariance as follows. So the expectation of xv prime of n should be exactly be given by the Green's function. So the expected value when starting in V of the number of visits to V prime of the simple random walk before exiting my box. And as we are in 2 dimensions, this Green's function actually behaves like a logarithm. So these are maybe 3 very standard models. They are also models which are, which seem to be a bit further away. And one of them, which I would like to mention, is actually the Riemann Zeta function. And of course, there it's a bit more work to see why it should be log correlated. But so what is the Riemann Zeta function? So the standard definition of the Riemann Zeta function is that we look at the sum n goes from 1 to infinity, 1 over n to the s, right? And the real part of s is larger than 1. Then this sum makes sense. And there's another way of writing everything, namely as a product over primes, 1 minus p to the minus s. And one can also make sense of this function outside of this region where the sum is really well defined. And what one is actually really interested in is understanding the Riemann Zeta function on the critical axis, namely on the line 1/2 plus imaginary part. Right? And okay, so the Riemann hypothesis is somehow related to the zeros of this object. What we will be looking at in this mini course will be more going towards the extremes. But what is interesting is now, if you now choose an interval of length 1 uniformly from some large interval 0 capital T, large, and you look at the Riemann Zeta function on the critical axis, where now T is in this interval of length 1, then this object really shares many characteristics of a log correlated field. So this looks very much like a log correlated field. Even though the only randomness I've put in is the choice of this interval and where exactly I look at this function. And in fact, it can be very well compared in a sense with this branching random walk, which was my first example. Another set of examples comes from the area of random matrix theory, namely for a larger class of random matrix ensembles. If you look at the log of the characteristic polynomial, and this is actually true for a certain class of random matrix ensembles. For example, the CUE. Then this looks like a log correlated. So CUE means you take an n by n matrix, which is unitary, which you sample uniformly from the unitary group. And you denote by P un of theta the characteristic polynomial. Then the logarithm of the modulus is essentially a log correlated field. And in fact, there are lots of predictions on how this Riemann Zeta function looks like. And many of them actually based on an analogy with random matrix theory. So there's somehow also a strong link between this example 4 and 5. Okay. So this should have given you some flavor of types of, this should somehow have shown you that there are many models that fall into this class of log correlated fields, and that, well, they tend to appear in different places. And what is kind of nice is that there are some general tools that you can maybe develop in detail for maybe the first example. And then you can try to use the same methods to look at the other examples and understand these models, which have various degrees of difficulties, of course, in more detail. And this is somehow a little bit what we would like to do in this mini course. But before we get really started, let me first come to the second part of the outline, namely what are actually the questions we are interested in. So The first thing one might be interested in. So, okay, so a lot of these models, so a lot of motivation to study these type of models actually comes from statistical physics, where these log correlated fields somehow appear as toy models for disordered landscapes, energy landscapes. And in these energy landscapes, what you really would like to understand are, for instance, level sets. Right? So maybe you want to understand, you have this physical system, it's log correlated. You maybe want to understand how many sites you have that have, where the energy is roughly equal to a certain value. And what has been a very prominent theme in understanding log correlated fields in detail is actually the study of the extreme values. Okay. And when I mean extreme values, of course, there are a lot of questions that build on each other. Right? So first of all, you could ask for a law of large number type of result. So you could ask for the rough order of the maximum. You could also try to be more precise. So is there really, can you say that the maximum is roughly really a function of, so a non-random function. So let's just say the maximum is roughly equal to some expression plus order 1 fluctuations. Where with expression, I mean that it should be a non-random function that only depends on the size of the system, right? So you can say, I don't only want to know what is very roughly speaking this first of the maximum, but I want to know it very precisely. And if I know it very precisely, I can even ask, can I describe all particles that are close to the maximum, or all sites that are close to the maximum? So I can ask for the extremal process, and then I might also be interested in, okay, but now how many are there? So I might be also interested in more quantitative results. And even if you just look at the 5 examples I've given you above, so the first question is, of course, the easiest, and it's essentially answered in all of the above. But even if it comes to this fluctuations and understanding how does the maximum really look like, in some of the examples I've given you above, this is not really well understood because it's actually hard. You need a much more detailed information on your process. And well, in essentially the first 3 examples I gave you, you also have access to the last 2 points. In the other ones, that's very challenging. But there are some nice tools there. And a third set of questions that I meant is actually the connection of log correlated fields to Gaussian multiplicative players. I will mention this in the following days only on the site, because Nathanael already gave a mini course this summer on this. And so, very roughly speaking, what you could do in connection to Gaussian multiplicative pairs is you can look at the exponential of gamma times your favorite field of the above. And now you can somehow right? And now this somehow depends on some kind of location, and you can somehow, turn this into a measure. Be very, very sloppy here, and let's just, pretend I take the back measure, but you can somehow turn it. I mean, okay, in some of the models above, you actually need to sum over all leads that you have, because you don't really have a second dimension. And sometimes in the Gaussian field, you can actually really look at these things as measures, right? So let me put this in quotation marks, and you can look, right? But for instance, for the characteristic polynomial, this makes perfect sense. And you can try to understand this measure better. And in particular, if you look, for instance, at the logarithm of a characteristic polynomial, right? Because there it's really indexed by the whole space, you can ask yourself, how does this behave if I make the size of my matrix very, very big? So I can ask somehow, is there, first of all, if I take the size parameter to infinity, I can ask myself, does this object converge when properly normalized? And the answer is that, well, if gamma is smaller than some gamma critical, then usually the limit object is a particular Gaussian multiplicative chaos that comes from the Gaussian field that matches the limiting covariance. And if I have a gamma which is larger than this gamma critical, then to understand the limit, right? Actually, the extremes are important. And there are also some nice connections between the level sets and this Gaussian multiplicative chaos. But somehow in this course, I will focus mainly on this part and leave this last part out a bit, also because we don't have that much time. But I at least wanted to mention that this is actually also an interesting line of research, and that there are many things to do. And that, for instance, for random matrix theory models, it turns out that actually looking at this third question is something kind of doable, because it matches nicely with some models. Because it matches nicely with some models. Some methods that are used in random matrix theory. So I've introduced a lot and said a lot about what the questions are that we are looking into. So let us start actually to try to understand a little bit the extremes. And to give you some idea of what is actually going to be somehow important there, I will start with a very direct I will start with a direct computation to give you a little bit an idea of how these computations. And so what we will do, we will look at the binary branching random walk with Gaussian increments and n levels. And what we would like to understand is, can we find an upper bound on the maximum of this whole collection? Can I say something? Can I find some bound on the maximum value? So what I would like to look at is the probability that the maximum over all leaves, v in Vn, x Vn is greater than some value y, which we would like to choose later in such a way that we can say something meaningful. So now I would like to find an upper bound. And so in general, what turns out to be a good trick here is that I can rewrite this event that the maximum is larger than y as a sum over all leads, v in Vn. And now I can ask every single one of my leads, are you larger than y? So I say, if I put an indicator function, xv of n is larger than y. So this sum counts. So this sum here now really counts the number of particles above y. And so the probability that there is a particle above y is exactly the same as asking that this sum is greater or equal than 1. And now I can simply use Markov's inequality and say this is bounded by the expected value of the sum v is in Vn, indicator function xv of n larger than. But this expectation I can explicitly compute, right? Because okay, so I have, right, so because I have this sum I can pull out because it's just the sum. And then I have the expected value of this object. So I get the sum v is in Vn. Now I have the expectation of an indicator function. So I have the probability that xvn is larger than y. But now this probability only contains one of these x values and not all of them. Right? And so I know that all of these are exactly Gaussian with mean 0 and variance n. So this is nothing but 2 to the n times the probability that a Gaussian with variance n is larger than y, where this xn should now just be Gaussian mean 0 variance. But okay, so I have 2 to the n particles, so I know that the y should not be too small. And so for y large, I can actually compute this very nicely. I know that this is roughly 2 to the n, and now I use Gaussian tail formula. And I say, well, the probability that a Gaussian is large, well, this is roughly, and it has variance n. This is so for standard Gaussian, it would be 1 over x e to the minus x squared over 2. Now I have variance n. So if I do this, I have square root n divided by x. This is square root 2 pi, a constant. And then I have an e to the minus, and I shouldn't put the x here, but the y, so e to the minus y squared over 2. And if y is large, this is a very precise thing. And now what I need to do is, what we want to do is we want to find y such that this is essentially of order 1. Yeah. So we are bounding a probability. So whenever this thing grows to something which is not of order 1, well, then we just have a really bad bound. So let us try to find y such that this is of order 1. So if we look at this expression, right, the largest term, which is making it big, is the 2 to the n over here. And the best chance to kill this 2 to the n here is to use the y square here. And to make things a bit more, let us just say it. So we have this term from the Gaussian tail, square root n, square root 2 pi and y. Then this 2 to the n, let me just write it as e to the log 2 times n. And then I have minus y squared over 2. So if I want this term divided by 2n to cancel out this, I need in first order to make these this term equal to 0. And if I do this, for this, I want to choose y to be roughly square root of 2 log 2 times n. Because if I square this, I get an n square. One of the n cancels and one stays. Right? And this square root 2 log 2 squared divided by 2 gives me exactly this log 2 over here. So if I plug this in, then this becomes 0. But of course, I still have these terms over here that I need to take care of. So my first guess is, well, I have to add something which is of smaller order. Right? And now this smaller order needs to be such that the square root n over y also disappears. And so what turns out to be the good choice to make this really of order 1 is that you choose y to be square root 2 log 2 this times n minus 1 over 2 square root 2 log 2 times log n. And if one plugs this in, one sees that the mixed term of y squared is exactly tailored to this expression, right? Because this, you can maybe just do this by yourself, because otherwise it's a bit too, it will take a little bit too. So this is a good choice. But to make this object of order 1. So if you choose, so if we take a large constant, and we take y, if we choose the y to be what I've just written to make this of order 1. Plus this large constant, then the probability that the maximum of x v of n, this is larger than y. Becomes small because I've added this extra large constant. Yeah. So we have, as a result, this y, right, with some large constant. So let me just write this as some big correction. This is the first upper bound on the maximum for the branching. Now, what is very particular about this? Well, note the following. We have not used anything about the branching random walk. The branching random walk, right? We also could have done exactly the same computation. So apart from that, we have 2 to the n random variables, and each of these random variables is the Gaussian with mean 0 and variance n. And we could have done exactly this. For instance, we could have done exactly the same computation. Exactly the same computation with 2 to the n with 2 to the n IID with the matching variance. And one can convince yourself that the answer that we got as an upper bound, right? So in fact, this square root 2 log 2 n minus 1 over 2 square root 2 log 2 plus 1 is the order of the maximum of 2 to the n IID Gaussians. So we see that somehow with this Markov inequality, so we somehow see that with this Markov inequality, we get that, well, due to correlations, the maximum is not higher than in the independent case. And somehow what we would like to understand now is this actually a good answer? And so, in fact, the true answer for the branching random walk is that the maximum is roughly 2 log 2 n minus we to log 2 stick to color log 2 log n plus a correction of order log. So actually we see that this upper bound that we got is actually 1, in the sense that the sense is that the first term that we got is correct, right? That's the first order, but the second one is different, and we get this 3 instead of the 1. And what I will try to convince you today, that actually, what I will try to convince you of tomorrow, is where this comes from and how these type of things could be addressed with path localization. Because what we have not used Well, if we look at this at a previous level, right, at some level k, well, at this level k, we don't really have 2 to the n. We don't have 2 to the n leads, right? We only have 2 to the k portions with variance. Right? So somehow we should be, so somehow what we will need to take into account is the fact that we don't have 2 to the n particles all the time, but at previous times we have less particles. So at previous times, we cannot have a path that's really high. And this is somehow what we will try to do better. Better tomorrow. And that's all I wanted to tell you today. So tomorrow, what we're going to do is we're trying to go to understand this better, where this 3 actually comes from, and what we can do with path localizations. And yeah, I will just stop here. I'm happy to answer questions in case there are some.
Okay, thank you. We can all unmute also to thank Lisa. And I guess one sort of question related to this. So this factor of 3 there. So this is there is some universality of that, right? In that
Yes.
Can you say a bit about that?
Yeah. So it turns out that it turns out that there is a certain universality in this 3. So somehow in all log correlated models, if you look at the corresponding, you look at the corresponding IID setup. Right? So you match the variances and you match the number of random variables that you need. Then the maxima differ. So the maxima have the same first term. And in this second order term, which is this logarithm, so which is logarithm of n somehow, in this second order term, what you need to do is you need to always replace the 1 with the 3. Right. And this is somehow this is somehow universal, but it comes a bit from the fact that you believe that this branching random walk is like the stereotypical log correlated field, and all of the other ones can somehow be approximated on the level of the maximum by this one. And then this effect that 1 turns into a 3, so I will explain this tomorrow, is essentially telling you that if you look at that, you can somehow look at the path to the maximum, and this constraint that you have fewer particles at the beginning means that the path to not go above 0. I mean that you have a Brownian motion, you have this walk with a drift, and you essentially condition in some sense now a random walk to not go above 0. And this is going to cost you exactly this additional 2. But I will come to that a bit more tomorrow.
There is also a question in the chat that has been pending of Sergei Pirogov.
Maybe just, okay. I have it here. Yeah. So in what sense is the branching random walk log correlated? So
I answered it to Sergei already. I answered it already.
Okay.
But maybe you should make this remark, maybe that is actually sort of helpful, that really this logarithm refers basically to the metric entropy. So for the number, it's the important thing is the number of sides which are at a distance, and the logarithm, and so in the logarithm of that is basically just presenting this is what you have to look at.
Yeah.
So in the case of a Gaussian free field, of course, that's the same because it's just polynomial. But in the branch in random walks or so, this is growing exponentially, and so the logarithm becomes a linear of an exponential function, becomes a linear function. So it looks a little bit different.
Yeah. So in branching random walk, you have 2 to the n particles, and so on the ranks n. So somehow, if you take the logarithm of this 2 to the n, you get something linear, and that's why. Yeah, and that's why the covariance actually doesn't really have this log there, but it's still somehow a log when measured in the number of particles. And what is important is somehow if you take 2 particles, is the number of particles that have now a certain overlap. And that is somehow the logarithm of, this is somehow on the logarithmic scale of the number of particles. Are there further questions?
Well, okay, yeah, if there are no further questions today, then
Okay.
we will resume tomorrow.